Okay, it is 12 o'clock. Hopefully it is streaming well. My name is Richard Kaur, and this is Lecture 3 for MAE 113, Calculus for the Liberal Arts. In this lecture, we'll be continuing our review of previous material that you should have seen in 103 and from high school. We have a couple of comments or questions that I saw in the live chat already. The problem set or the assignment has been posted. It's, I think it's just called Assignment 1. It's a PDF file, and it's just simply a list of questions from the textbook to try out, and the answers are at the back of the book, and I mean towards the end of the PDF of the textbook. And also there is a solutions PDF as well, so you can always check that out if you get stuck. Another person has asked if how the quiz is going to be conducted. At least for next week's quiz, we'll be doing it over Moodle, and I hope my streaming is doing well enough. Can everyone see me or hear me okay? Because I just got a message saying that YouTube is not receiving enough video to maintain smooth streaming. So okay. Whew. Yes, welcome to the age of streaming. Okay, so without further ado, let's not waste any more time on seeing if the internet is working. So let me just finish off some examples that we had done last time. Examples. Okay. So this was from page 19 and 20, and again, the textbook is posted online. Let's find all the numbers x such that x squared is less than 9. Now, a way that we can do that is reduce it back to how we were solving inequalities before with 0 on the right-hand side. So again, we could bring that 9 to the left-hand side. So it becomes a negative 9. We have x squared minus 9, and we see that's a difference of squares, so we can factor that. So I get minus 3 and positive 3. And just doing a quick little sketch. I know that this is a parabola, and the constant or the coefficient in front of it is positive, so it means that it's opening upwards. It has zeros at minus 3 and 3, and to see that, you just do x plus 3 equals 0, x equals minus 3, x minus 3 equals 0, so that means that x is plus 3, and it's opening upwards. So just a quick sketch. And what we're looking at is that we want it to be less than 0 at this point. So it's all of this graph part right here, which is less than 0. And it has to be strictly less than 0. So that means that for this, its x is between 3 and minus 3, and that's the answer. Perfect. Now, if we need to find all the numbers x such that x squared minus 2x minus 3 is greater than 0, again, we can factorize that. Breaking that down, it becomes x minus 3 and x plus 1. Again, it's still a quadratic. That is opening upwards, -1 and 3, and again. But this time it's asking for us where it's greater than 0. So it's all of this part here in the graph. So again, it's everything that's less than -1 and greater than 3. Okay, now there's things in calculus we will be referring to a lot of intervals. So we actually have interval notation that we'll go through. So in the textbook, this is in review section 2, and this is intervals. And absolute values. Okay. Okay, so there's actually like 9 different interval types, but for instance, we use an open dot to mean that it doesn't include something. So if this was, say, our number line, and we'll say A and B, this would be, if we wrote it out kind of in our this notation above here, we could write that as it's all the x's that are between A and B, but it doesn't include B's. So that's why we write these little circles. They're little holes. And the way that we think of that is we can also write that in kind of a shorter notation. Instead of having to write that out, we just write it with round brackets, A, B, and then the round brackets, which is a little different than there's might be some people who've studied in French, and they'll have some different ways of writing the interval notation. But in English, we usually use the round brackets. And, okay, well, we can do the closed. And again, same idea. This would be the x between A and B, but because we've closed it, it's less than or equal to. And when we have these holes filled in now, so we have these solid dots, and we use, for the interval notation, we use square brackets. You can get different combinations of that, so you can get, say, like A and B, one with an open hole and one with a closed hole, so that would equate to A less than X less than or equal to B, and then we can write that as in bracket, like these parentheses notations here. We have a round bracket A, comma, B, close bracket. Okay. And we can, we can switch them. We could actually have a closed hole here. It gets more tricky when we get to infinity. So I could have it closed here. So here's A, and it goes off to infinity. I can say that a is less than or equal to x, and then less than infinity. And so again, infinity is not a number, it's a concept, and we just kind of use this as a symbol to represent that. We can never actually get to an infinite horizon. So when we do that, we have a comma infinite close bracket. Same thing can happen over here, which then have infinity going over here. And that's the negative infinity. So we can have minus infinity less than x less than or equal to a. So we can actually have it as infinity comma a square bracket. And again, let me just see, make sure here's number 2. We can also, the same thing happens for the open holes as well. So you can have an open, we have a, and that means that we have a to infinity. We can have same thing, we can have minus infinity to a, and we can actually have infinity to infinity. So it's just minus infinity to infinity, and that's it. Oftentimes you'll see me say something along the lines of that x, say if x was in, say, here, no, it's in this interval, what you'll find is that I'll write x is an element, and that's what the little epsilon means in this case. It means that it is an element of the interval from minus infinity to infinity, or equivalently, some people might say that from minus infinity to infinity, it'd be over the entire real line. Okay, put that over there. So here are some examples. If we start to use interval notation, you know, here's a quick question that could show up on a quiz or a test. Not the exact question, but again, the style of the question is. So for instance, 4 is an element of the interval from 1 to 5. Is that true or false? What does everyone think in the chat? Is 4 in the interval from 1 to 5? Good, true. Yeah, good. That's good. And remember, there's a little bit of delay. It's not like it is. It's true. So, again, I think there's about a 20 to 30 second delay. But yes, it is true. Good. Same thing. Here's 1 is an element of the interval from 0 to 1. Is that true or false? I have 1 false so far. That's At least that's an answer. Good. Anyone else? Yeah, false, false. Good. Good. I like to see that everyone's saying false. And the reason for that is if I draw out the little pretty picture for it, the little interval diagram from 0 to 1, this 1 isn't included in it. There's a hole in it. So we use the round bracket. It's 1 is here, but it's not included. So that is false. You might see other, sometimes I will say, if I was writing this, it's not my question, I would say that 1 is, I'll put a line through it, not an element of 0, 1. Okay. And as a review from last time, 4 minus 5, is that an element of the natural numbers? Good, yeah, it's not. And the reason for that is, well, 4 minus 5 is minus 1. And the natural numbers, if we remember from our first lecture, is 1, 2, 3, 4, 5, so on. And again, those are the natural numbers. And it doesn't include the negative numbers. The negative numbers are integers. So no, it's a false. So you could say that 4 minus 5 is not an element of the natural numbers, but you can say that 4 minus 5 is an element of the integers. Good, 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 good. Okay. What's another thing that we can do? Do natural numbers also include infinity? Do natural numbers include infinity? And the answer is there's infinitely many of them. There's countably infinitely many of them. And they go on to infinity, but I'm not sure if I can say if it includes it or not. I would say no. It doesn't include it because there's infinitely many of them. When we get into higher courses up in analysis and real analysis, which is kind of like calculus on steroids, we sometimes have to think of infinity as a number. We call it the extended reals. We actually make it include infinity, but again, that is beyond the scope of the course. I would say no. In this case, it does. In our course, the reals do not include infinity, and in this case, the naturals also wouldn't include them. Okay. So let's consider an example. There's if I have A is less than B, which means that I have something like, okay, perfect. That is the problem with mathematicians. We have an inability to lie, and we don't want to tell you anything false. Okay, so that means that if a is less than b, then a plus b over 2 is an element of the interval ab. So essentially what this is asking us to do is they're asking us, is a plus b over 2, is that between a and b? And this ends up breaking it down into two cases. So we'll have like case 1, because we have basically, you treat these as inequalities. They're inequalities, but there's two of them, and we treat them as such. So what we do is we need to show that a is less than a plus b over 2. Okay, and we need to show that, and we start off with our starting assumption, which is a is less than b, which is fine. The next thing that we're going to do, because we were trying to manipulate so that we get it to look like something like this at the top here, what I'm going to do is I'm going to add a on both sides. So I got a plus a is less than a plus b. So again, I haven't done anything wrong. So I can do 2a is less than a plus b, and I'm almost finished. I can divide through by 2 on both sides so that I get a plus b over 2. The second case, then, we need to show that a plus b over 2 is less than b. So again, we start off with a is less than b, but instead of adding instead of adding a, which we had done in the first case, we're going to add b on both sides. So we get a plus b, so b plus b, which is 2b, and dividing through by 2 by both sides, I get a plus b over 2 is less than b. And then I can combine these now that I've done the two cases. So therefore, a is less than a plus b over 2, which is less than b. So again, that means that in somewhere along this point here, I have a plus b is over 2. Oh, and I smudged it. Oh yeah, and terminology. The 3 dots is a shorthand form, usually for therefore. And, oh yeah, I guess you can call this a proof. And I usually finish off with a little mark at the end, just to say that, yeah, I finished it. What we've done here is you can read it mathematically, but what you can actually look at it is that in kind of plain English, I have no idea why there's a propensity for people to be afraid of numbers or to express things in symbolic form, but part of your job will be to explain either to higher ups or lower downs the meaning of these things. And what we basically have done is, this is an average. We took A and B and we averaged them. And so you could actually say it's the average. What we've proven, or what we've shown, is that the average of the endpoints lies within the interval. And that makes sense. You know, if you had grades, you had one person who had 10% and you had one person who had 90%, well, then I would expect that the average student would be between those two extremes, right? So I have 10, I have 90. So 10 plus 90 is 100, divided by 2 is 50. So yes, it's in between that. If there is something that's too abstract, always bring it back down to a concrete example. It can be helpful. Okay. Now that we've done that, this is following page 22, and we talk about the absolute value. Okay. So the absolute value is a way for us to make sure that a number that we always are getting is positive or 0. So what I mean is that we use these absolute bars. We use, here's an example. So I write 3, and then I put these long bars beside it, in front and at the end. And it's basically, it throws away the negative sign. So if I see 3, okay, that's fine. I can just write 3. If I see negative 3, I throw away the negative. I don't worry about that. If I have minus 2 times 5, okay, well, I do the inside here. I have parentheses around these, order of operations, so forth. So I have minus 10, and then I just throw away the negative sign. Now, we can express this mathematically. It's a little weirder as a function. We can say that we take any number, say x, and it's going to be the same. So in this case here, if I had 3, it's positive, it's still the same thing. So I'm going to say if this number x in here is positive, it's just going to stay the same. So that's if x is greater than or equal to 0. Similarly, if I have a negative, I have, this is called like my x here that I'm going to pass into here. So in this case here, I have minus 3. What I would like to do is, to using my original thing here, I want to just kind of make this equal to minus 3. And that becomes 3. So you notice here, I took this original input here, and I've just put a minus in front of it. So I'm going to do the same thing. If I'm passing in an x that includes a minus in it, I want to have another minus to cancel it out, and I'm left with then the positive number, and that's if x is less than 0. Now, I know in the book we haven't gotten to graphing yet, but again, this is review, so we should have seen it by now. We'll graph it. Here's my y and here's my x. And so again, it's going to be positive. So there's my absolute value. So y equals absolute f(x), Now, in here, we don't want to have negative signs. So what we're going to do instead is we're going to reflect it. There we go. And that's what happens. So if I have a negative number here, say -3, the value of that is going to be 3. And same thing over here, then if it's positive, we just leave it alone. And this would be the absolute value function. So this is kind of important. I should probably I'll put a box around it or something. Let's use green. Okay, so the next thing that we can do is here's describe the interval of x minus 4 less than or equal to 5. Okay, so I mean, if you don't want to think about this at all, then you can memorize a formula. And the formula is that a minus r, so this is the closed interval because we got the less than or equal to. I have a minus r, a plus r, close. This is the interval, and that's when x minus a is less than or equal to r. Okay, so that means that just using this formula here, we see that a is equal to 4, r is equal to 5. So then to make that interval, that is equivalent to me writing 4 minus 5, which is -1. And the same thing, I have a plus r, so 4 plus 5 gives me 9. In general, I don't usually remember that. Usually what I end up doing is I end up thinking of it in the two cases. So again, this is one way to do it. But again, I don't usually remember things. So if I was looking at this, I had x minus 4 less than, or sorry, this is the absolute value of x minus 4 less than or equal to 5. I have to think of the two cases. So again, I think of, since this is inside of the function here, I have to think of this when this thing is greater than 0. So if that is greater than 0, I'm just thinking of x minus 4. And the one thing that I want to do is I want to get up to that boundary, or I want to get up as close to that endpoint as possible. So I would say it's equal to 5. And I can solve for that. Is equal to 9. And then I also think of okay, what if in the inside over here it was negative? So I have minus x minus 4 is greater than 0. So I distribute that I distribute that negative sign, so it's minus x minus minus 4 gives me positive 4. Oops. And oh, sorry. What I was meaning was that if this was less than 0, then I would have x minus 4 is equal to 5. Again, I distribute that. Minus 1, x, and that negative sign comes over to the right-hand side, and so I have my 2 endpoints there. And so from that is how I would write my interval, so from minus 1 to 9. So both ways are fine. If you like memorizing things like that, you can use that. If not, you can think of the two cases, which is going back to the original definition of the function and finding what the endpoints were. Okay, so we did that. How am I going to tie this back to what we did previously was, oh, okay, yes. Page 4. So the next one was describe the interval for 9 as a single inequality involving the absolute value. Okay, so what I'm going to do then is I'm going to find that midpoint, and we know how to find the midpoint or the average, which is a plus b over 2. So the midpoint, so we have this interval here, we have, and I better draw this correctly. And what we want to do is then we're going to find a midpoint, say in the middle here, and then it's going to be plus or minus on either side. So then we'll have to find a distance from that midpoint to the endpoint, and that will give us our R. Okay. So to find the midpoint, it's 4 plus 9 over 2. 9 plus 4 is 13 halves. I'll leave that. So it's 13 halves. And then we need to figure out what the distance is from 13 halves to the 9, or we could have done it to the 4. And the distance between that is, well, it's 9 minus 13 halves. Or writing it over 2. 9 times 2 is 18. 18 minus 13 gives me 5 halves. So there's 5 halves here. So what I can do is I can express this, 4/9 is x minus, I have a midpoint, which is my 13/2, is less than 5/2. Now, you might be asking me, why am I not using the less than or equal to? Well, that's because in this case, I have square brackets, and in this case, I have round brackets, so I don't want to include the endpoints. And again, I drew them with the open circles there as well. Okay. There are some properties of the absolute value as well. The absolute value. The first one is the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Now we can think about that. For example, I mean, it's fine if they're both the same sign. So if I had 2 plus 3, which is 5, that's okay. There's 5 on the right-hand side, and I had 2 plus 3 on, so I would have 2, and that's still positive, plus 3, that's still positive, and then I add them, that's 5, then they're equal on both sides. But for instance, if I let x equals 2 and y equals minus 3, again, if they're different signs, then on the left-hand side, I have 2 plus minus 3, which is equal to minus 1, and then I drop the negative sign, so it's just 1. And then on the right-hand side, I have 2 plus minus 3 is equal to 2 plus, I drop the minus side here, so I get 3, and that's equal to 5, and yes, for sure, 1 is less than or equal to 5. So yeah, I could be like, therefore, 2 plus minus 3 is less than or equal to 2 plus minus 3. Okay. This is just multiplying, so if I take the absolute value of the product of two numbers, it's less than if I had multiplied them individually. And the last one that's interesting, which is the absolute value of x is equal to the square root of x squared. And we end up using this trick sometimes in programming when, for instance, we don't have the absolute function available to us in a programming language. So what we would do is we would square it. Squaring something always makes it positive or 0. And then taking the square root of it brings it back down to x. And if you were wondering what I was, for instance, if I had minus 2, well then I could say minus 2 squared all square root. I do the inside, so that is equal to 4 square root, so the square root of 4, which is still 2. We have the law of exponents. So this is section 3. So we usually, when we're talking about really quick multiplication, so instead of writing 3 times 3 times 3, sometimes it's quicker for us to say it's 3 raised to the power of, there's 3 of these. So we write it up in a superscript. So we have a base and we have the exponent. Just some terminology. And we have the rules that are listed in the textbook as well. So we have, if I have b to the m times b to the n, that's equal to b to the m plus n. So again, that would be something like 3 squared times 3 to the 4th. That's equal to 3 to the 2 plus 4, which is 3 to the 6th. Number 2, if I have b to the m to the n, that's the equivalent to b to the m times n. So I have 3 squared, let's say to the 4th, that's equal to 3 times 3 to the 2 times, sorry, 3 to the 2 times 4, which is 2 times 4 is 8. If I have a times b, so the base is ab, and we raise it to the exponent n, that's equivalent to a to the n, b to the n. So I could have something like 2 times 3 to the 4th, that's equivalent to 2 to the 4th times 3 to the 4th. Okay, another rule that we have is that any base raised to the 0 is equal to 1. Except for 0, 0 raised to the 0 is not defined. Number 5, b to the minus n is equal to the reciprocal. So if I have a negative exponent, I can just shove it into a denominator. And lastly, I have 6, which is b to the m divided by n is equal to b to the m 1 over n, or I could write this as b to the 1nth times m, or you can also write this as b to the m of the nth square root. Okay, I have 1 minute left. I think I will stop at there, but are there any questions before we sign off? We have the assignment is posted on Moodle, assignment 1. Our quiz is next Tuesday. I would recommend you follow and work through the exercises that for the sections that we've covered. And it should be straightforward because, again, this is review stuff. The office hour is going to start at 1 o'clock till 3, so 2 hours. If you have questions, I'm going to try using Big Blue Button. We'll see if this works. If not, we'll switch to a different platform. And if there's no more questions, feel free to send me an email at richard.kohar@rmc.ca. And if you have any questions, feel free to drop by during the office hour. Thanks again, everyone, for joining, and I will see you on Monday. Take care.